Okay, let's start with second part of topic of basic differentiation, which is required for understanding physics. So we are only dealing with basic differentiation to the extent it is required for physics. In continuation of the previous topic, let's look at one application of differentiation for a purpose of approximation. So what is the function given here? Y is equal to x cube, which basically means value of y depends on x, or y is a function of x. What kind of function? Is a cubical function. And what we need to find here, we need to find dy by dx at x equal to 2. There's another way we can interpret this question. Dy by dx is nothing but slope of a tangent. And which point we need to find the slope of a tangent drawn to the curve at x equal to 2. That's what we need to find here. So there are two ways of understanding the question. One is, of course, this equation is given. For each value of x, we can find the value of y. We can plot the graph. And let's see if this point is x equal to 2. And this is the corresponding point on the graph. So this is y value corresponding to x equal to 2, which will be 8. Y will be equal to 8 here. Okay, so what we need to find, if I plot the graph like this, if I draw a tangent at this point to the graph, slope of tangent is what we need to find. That is a graphical way. But mathematically, I can find the slope using concept of differentiation. What is differentiation or derivative? Differentiation, if I take 2 points, and if I draw a line joining, passing through 2 points on the curve, if 2 points are negligible distance apart, it becomes a tangent. That's a concept here using. That's a concept what we developed in last session. And how do we do that? Dy by dx is equal to, so value of y, we substitute value of y, because y is a function of x. It can be written in form of x, which is x cube. And d by dx, or derivative of x cube, is 3x squared, based on the formula d by dx of x raised to power n. Here n is equal to 3. It is equal to nx raised to power n minus 1. So n is equal to 3. So power becomes the coefficient, and then power of x is reduced by 1. Exponent is reduced by 1. So we find this derivative. Let's try and understand what is significance of derivative. What are the different purposes it can be used for? So what is value of this derivative x is equal to 2? This expression gives you slope of tangent drawn at various values of x. Any value of x we can choose. But we are interested in which x? X is equal to 2. So we substitute x equal to 2. 2 square is 4 into 3, 12. So dy by dx at x equal to 2 is equal to 12, which means there's another way to understand. What is other we can understand? What is dy? If I multiply, take dx here, dy is equal to 12 times dx. So how do I interpret this expression? This expression dx means a small change in x. And dy is corresponding small change in y. Okay, they are related. So if I make a small change in dx, change in y is 12 times. For a small change in dx, change in dy is 12 times. That's what it means. And we see how do you use it. That's how we have understood slope or derivative. And let's see how we'll see later how to put it to use. So what is 12 in terms of graph? So red color line is the tangent drawn to the curve at x is equal to 2. Slope of this tangent is 12. That's what it implies. And look at this blue color line is the curve, red color line is the tangent drawn at x equal to 2. If I look at a small area or a small part of the curve in the vicinity of point of tangency, this is point of tangency, this is a part close to the point of tangency, we find that tangent and the curve almost overlap, which again is according to our previous statement. If we take a small part of the curve, it is just like a straight line. Which is straight line? So we say in the vicinity of point of tangency, the curve can be approximated as tangent. Okay, and you can visually see that also. And suppose now let's see its application. So we can use this application, this 12 times application, find the approximate value of 2.01 cube. Now suddenly some of you might think, where from this question has come? So we were dealing with something like this. Yeah, there's some relationship with what we have been doing here. We are talking about cube of a value. So what is the cube of a value? So this expression also cube of a particular value of x. This expression is similar to the previous one. Only thing x value is 2.01. We know something like 2 cube is easy to find, but 2.011 cube is not so easy to find. We have to multiply by 3 times. So let's see how to use approximation. So what we know, see, corresponding to x equal to 2, this point is easy to find. If I take another point here, which point I have taken here? Here is 2.01. What we need to find? One need to find what is the corresponding y value. Okay, so what are you going to use here? These 2 points, they are close to each other. So let's use, can we apply this concept here to find this particular value of y, which is, can we find the value of 2.01 cube? You can also think before you proceed with the video. You can pause and think and then proceed. How do you approximate? What I have done to understand better, I have just magnified or zoomed into this part. So these are 2 points on the curve. This is corresponding to x is equal to 2, and this is x equal to 2.01. This point is 8, and this point we don't know. This point we need to find. And what is the slope? Slope is equal to 12 here. Or another way to understand, if this is 2 and 2.01, what is the value of delta x? Delta x is equal to 0.01. So what will the delta y? That's what we studied here already. Delta y, what will be change in y if x increases by 0.01 from here? When we go to this point, x increased by 0.01. What is the corresponding increase in y? Corresponding increase y will be 12 times of 0.01. So delta y will be 12 into 0.01, which is equal to 0.12. So what will be the value of y corresponding to x equal to 2.01? This value will be 8.12. That's approximation. So let's see what it means. That's what he had done. So what he had done, same expression. I'm using y is equal to x cube. Which point? I'm using it near x is equal to 2. So I put x equal to 2, 8 is equal to 2 cube. What we need to find? We need to find value of y corresponding to 2.01 cube. This we know. This is another point close to the previous point here. That's what we are using. 2 points close to each other. So x has increased by 0.01. As rate of increase of y is 12 times the increase in x. So what will be this value here? As x increase 0.01, y will increase by 0.12. So what would be this value? This value will be equal to 8.12. That's the approximate value of 2.01 cube. And we have arrived at this value without actually using the cube. We are not multiplied by 2.01 3 times. 2.01 into 2.01 into 2.01. By very simple mathematical calculation, we approximated this value. And if we actually calculate using a calculator, actual value is 2.1206. You find, so this, what you notice here, this approximation is very close to actual value, and that's the power of derivative. It gives you, for a small change, it gives you rate of change, which is slow. And that's a useful application. And right now, we are not going to dwell too much on this. See that this concept is understood. See that this 3-4 points here, all the points are small, several points that are discussed, all are clear to your mind. One more important application is understanding of graph. We can understand graph in terms of slope. And what kind of graph we talk about? Yeah, easiest form of graph is straight line, which is a constant slope. But which is not a straight line, curve kind of shape. How do I understand better in terms of what is happening to the slope? It is not a straight line. It means curve slope is changing. If slope is changing, it can increase or decrease. Let's understand that part. And the reason I am discussing it here, it finds application in physics in many cases. Let's go on. What I have done here, I have drawn two curves here. Each curve represents one particular function. Which are two functions it is representing? One is representing y is equal to x square and y is equal to root x. They're two different functions. So one of them is represented by blue color, other is represented by pink color. And what you notice here, both curves intersect at which point here? This curve intersect x equal to 1. And you notice if I put x equal to 1, value of y is equal to 1. Even here also substitute x equal to 1, y has same value. Thus, this is the point of intersection. And we can easily find through substitution, this curve represents y is equal to x square. And this curve is y is equal to root x. And these two curves has a different shape. And let's understand the shape and how do we understand the shape better in terms of derivative and what can we learn to identify the shapes better for any such function. So what is the objective here? Whenever this kind of exponent y is given in form of a sum power of x. We should be able to visualize the shape of the curve. The shape of the curve is something like this or like this. It will be two shapes. Let's understand what those two shapes are and when do we get which shape. So since we are talking about slope of the curve, we'll take the derivative. Derivative of first function is 2x. Derivative of this function is 1 by 2 root x. So we should understand this function I could have also written as x raised to power 1 by 2. So in this case, we can find this derivative using n is equal to 1 by 2 and this expression. I'm not going to do it. You should practice yourself. These are the two derivatives. So this expression gives you slope for different value of x. So suppose I have to find slope at 0.2. Slope of this function at x is equal to 0.2 will be equal to 0.4. And accordingly, this function also. This is a square root. It is a little more complicated, but still we can calculate. So this is the slope here. So if I draw a tangent to both the curves at 0.2, so I have drawn to both the shapes. Similarly, I'll draw 2-3 points here, and let's understand what is happening to slope of the tangent. What you notice here, both curves are sloping upward, has a positive slope. And if I have to compare here, this pink color has a greater slope than the blue color, which is okay. I have drawn another tangent. The second one is drawn tangent at x equal to 0.4. Here also tangent drawn, here also tangent drawn. What I notice here, this tangent slope here is greater than this here. Whereas this slope, tangent of this slope is smaller, is compared to, so as x is increasing, let's take one more point here, what I make. This is the third point. This is as we go here, as x increases here, in blue color, the slope is getting steeper. In pink color, the slope is getting flatter. Slope is decreasing here. So here in case of blue color, this is the shape of increasing color. So imagine if this is slide here, here the slope is less. As we keep going, slope is increasing. So this graph represents positive slope. Yes, slope is positive. Everywhere, slope of tangent is positive slope, but it is not constant. It's not a straight line. If it is not a straight line, it has to increase or decrease. What is happening here? But increasing. In this case, increasing slope. So see that you understand the shape and you understand what I have written here. How about the slope here? So whenever we talk about slope, I'll use two terms to define slope in case of curve. Is slope positive or negative? Is it increasing or decreasing? In this case, here also, all three cases, what is happening? It is positive slope. But what is happening to slope? Slope is decreasing. In this case, but decreasing. So you notice here, by the time you come here, suppose this was a road here, this is like a very steep road. Suppose you are moving from here. Here the slope is more. As you keep moving, the slope gets flatter and flatter. But slope is decreasing. So we just try and visualize what this is the shape. All curves which is increasing slope will have something like this, and all curves having decreasing slope will have shape like this. Okay, so both are positive for all positive value x. So first one increases with x. And reason also simple. We can understand from the formula also. You notice as x increases, dy by dx will increase because x is in the numerator. Where if here x is coming in the denominator, and as x increases, denominator value will increase, as the slope will decrease. So I can understand from the graph also. I can understand from derivatives or the slope formula also. So first one increasing, second one decreasing. Can we generalize this result here? Yes, we can generalize here. In first case, what you have noticed, the power is greater than 1. Here, power is less than 1. So when does the slope increases? Whenever power is greater than 1, slope will increase. Shape of the curve will be like this. Whenever power is less than 1, slope will decrease. The shape will be like this. Just a generalization. The general result, when n is greater than 1, slope increases with x. We can again check with derivative. And when as n is less than 1, slope decreases with x. So far we have been dealing with only one type of function, and kind of it is something which can be expressed in general way. Y is equal to x raised to power n. N can be any rational number. Let's look at some other functions also and their derivative. So we are going to look at, so as you can see from the graph, we are looking at trigonometrical function. We'll start with sine function. So suppose we have function y is equal to sine x. So on x-axis here, y-axis we have, see, how do we get y is equal to sine x graph here? See, on x-axis we have angle, and as you can see, all angles are in radian, something like pi by 6. Suppose I have to plot the graph. I know pi by 6 is equal to 30 degree, and sine of 30 is 1 by 2. This value is 1 by 2. Similarly, for different angles, either I can read the value of sine of a particular angle from a table or from a calculator. We can plot this graph, and we have seen this graph earlier also. This is sine function graph. So this x-axis the angle, and y-axis corresponding sine function of that angle. So this graph we have plotted. Now, how do you find its derivative? What is dy by dx or d by dx of sine x? So again, more than derivation, what is important is underlying concept. How do you find its derivative? Derivative is slope of tangent drawn to the curve. So how do you find slope of the tangent? So tangent is basically, if I have to find slope at point x, basically this is, suppose we take this point x here, and at this point we want to find the slope of tangent. Actually, conceptually what we do, we take this point and we take another point at a negligible distance from here, very close to it, and we draw a line passing through these 2 points, a secant at 2 points on the curve, negligible distance apart. Since the distance is negligible, it decreases like a tangent. So if the distance is approaching 0, secant becomes a tangent, and that's how we find it. So 2 points and then slope. Let's do that point again. Let's repeat the same process here. So if this is x, corresponding y value will be equal to what? What will be y coordinate corresponding to x? Y coordinate will be equal to sine function of x. So y will be equal to sine x. Sine of, and similarly, what is second point here? We choose the second point at x plus dx here. So what is x coordinate? X plus dx. What will be corresponding y coordinate? Corresponding y coordinate will be sine of x quantity on the x plus dx, and which can be written as y plus dy. So what has happened? As the x coordinate, quantity x coordinate has changed by dx, quantity on y coordinate has changed by dy, and that's how we find the slope. What will the slope? Slope will be dy by dx. That's the slope of the tangent. Let's do that. Y plus dy is equal to sine x plus dx. What is dy by dx? Dy by dx is this quantity minus this quantity is dy, and this minus this dx. So what is dy? Sine of x plus dx minus sine x divided by dx. So this function, but here what is the dx here? Dx is tending to 0 or approaching 0. So that's what you have to use. That's one thing you have to use. And second thing here, to simplify this expression, we'll use sine of 2 angles. What is the formula for sine of 2 angles? That's what we'll apply. Sine of first angle, which is x, into cos of second angle, which is dx. And then we reverse the order. Sine of the second angle, which is dx, into cos of the angle, first angle, x. Whole thing divided by dx. And in this case, what we need to do, what is cos of dx here? This is a dx term which is tending to 0. So if dx tends to 0, it means this cos of dx also can be taken almost equal to cos of 0, and value of cos of 0 is equal to 1. Okay. And similarly, what is sine of dx? We have dealt with this part earlier also. If dx is expressed in radian, sine of a very small angle is almost equal to value of angle in radian itself. We have done sine theta can be approximated as theta if angle is very small. Okay, so this angle dx is very small, so it can be treated as equal to dx. These are two substitutions we make here. So what is the expression we get here? Sorry, minus this sine x is also there. Okay, so let's put these values again. So it becomes sine x. In place of cos dx, we substitute 1, plus in place of sine dx, it becomes a dx into cos x minus of the sine x divided by dx. So more than the derivation, you understand where does it come from. This conceptually, that's what we do to find derivative of any function. And analysis simplify, this 2 gets cancelled, dx gets cancelled, is equal to cos x. So derivative of sine x is equal to cos x, and So let's understand. So suppose I want to find out, suppose what is the slope of tangent drawn at x is equal to pi by 6. I want to find slope of this tangent. Okay. So can you find the slope of tangent here? So slope of sine x curve at x is equal to pi by 6 will be equal to, what will the value of slope here? Slope will, or basically what we are saying, what is dy by dx at x is equal to pi by 6? If x is equal to pi by 6, dy by dx will be equal to cos x will be equal to cos of pi by 6, which is 30 degree. What is cos of 30 degree? Equal to root 3 by 2. So basically, if we draw a tangent to sine function at point x is equal to pi by 6, the slope of tangent will come equal to root 3 by 2, cos of pi by 6. That's what the tangent. If I draw a tangent at this point, x is equal to pi by 6, slope of this tangent will be root 3 by 2, where root 3 by 2 will be roughly 0.87, 1.73 by 2. That's what this expression means. Okay, similar way, let's do one more. Suppose it's a constant function. If y is given as y is equal to a, what would be its derivative? What will be derivative of a constant? So derivative, say again, just trying to recall, differential derivative function is equal to slope of tangent at a point. That's one way to understand. Another way to understand derivative is rate of change of y, rate of change for a very small change in x. So basically, at what rate quantity on the y-axis is changing for a unit change in x. That's the rate of change. There are two ways to understand. And this also, this understanding is also important to understand some of the applications of derivatives. So suppose this is a function. Can you find its derivative? So with dy by dx here, y is equal to constant, is d by dx of constant. So what is derivative constant is 0. Let's understand why. So can we plot this function? Can you get a graph of this? Y is equal to a. So y is equal to a is something like this. For any value of x, y is constant. Okay, so this also can be written. I could have also written as, is it a function of x? Yes, it is a function of x. What is power of x? I could have written x raised to power 0. That's another way I could have written. See here, what we notice here, what is the slope? Slope is a constant. It means slope is constant, is a derivative of constant. What is the slope here? It's a straight line, and slope at all points is equal to 0. If slope is 0 at all values of x, it means its derivative is 0. So derivative of any constant is 0, which also means if function is constant, it is not changing with change in x. As the x changes, the function does not change, constant function. So rate of change is 0. It is not changing. Any constant, rate of change is 0 or its derivative is 0. So if y is equal to 5, we plot this one, y is equal to 5 at different value of x, y value will remain 5, 5, 5. So it will be a straight line parallel to x-axis, and its derivative will be 0. Slope will be 0 at all points. So very simple point, but important point to understand. Now let's find derivative of product of two functions. Let's first understand what is the product of two function look like. One simple example. So suppose I write y is equal to x sine x. You know, this x term is coming twice and is multiplied. So one function is sine function and other is a linear function with coefficient 1. So it's product of two functions. So I can represent, so this is one x term here and there's another x term here. So what we do in whenever we write a formula, we represent first function. Let's say first function is u function and second function is b function. So u and b are two function. Y is a product of two function of x. X is coming in two parts in form of a product. It could be any two function. Okay. So what is the formula here? We are not going to go for derivation. If y is product something like this, its derivative is equal to first function into derivative of second plus second into derivative of first. That's the formula. So let's apply this formula in one simple example. We are not going to derivation. And suppose y is equal to x sine x. So how do we apply this formula? This is first function, this is second function. So this part is first function and this I am taking a second function. So first function into derivative of second function plus second function into derivative of first function. We just put those values and now it is very easy. What is derivative of sine x is cos x and derivative of x is 1. So what is this expression? This becomes equal to x cos x plus sine x. That's how we find derivative of product of two functions. Okay. Let's see some more application of this. Can we apply product of two function to y is equal to a into x to power n? So far we have dealt with y is equal to x nth power of x. What if it has a coefficient here? So even this also can be treated as two function. So this is very simple formula, but this a is one function and x raised to power n is a second function. Is there x term here? We can assume for constant function x, there is x term with the power of 0. This first function, this is second function. So what is derivative of product of these two functions? First function into derivative second plus second function into derivative of first. So in this expression, derivative of constant is 0. So this term will become 0. The derivative of these two is equal to a into d by dx of x raised to power n. So what we have understood, so whenever we have to find a derivative of a function which has a constant coefficient, the coefficient can be taken out and then we can take the derivative of the remaining part. Okay, so constant function coefficient can be taken out of derivative. Something like this. If y is given as 4x cubed, what is its derivative? So when we find dy by dx, dy by dx could have been written as what? D by dx of, if we substitute y value, what is y here? 4x cubed. So constant can be taken out of the derivative. It can be written as 4 into d by dx of x cubed. And derivative of x cubed is 3x square. So it will be equal to 4 into 3x square. It will be 12. So let's take up some simple example of whatever we have done so far. Some simple kind of derivatives. So let's find dy by dx of following function. Each case you can repeat this one. Look at the question. You can pause it, solve it, and check it. Okay, so suppose we need to find derivative of this. This we have done a couple of times before. What is the derivative of this? How do we solve it? What is dy by dx? Dy by dx is equal to, put the value of y. It is d by dx of x cubed, which is equal to 3 into x square. So this is derivative of the first one, x square. Second one, if y is equal to 4x square, what is its derivative? Again, pause, solve, and check. Answer is 4x. How do we get 4x? It is d by dx of 4x square. And whenever this is the constant coefficient, the constant can be taken out of this derivative. So it is d by dx of x square. It is 4 and derivative of x square is equal to 2x. So that's how we get this derivative. Second one. Third one, dy by dx of 2 by 3x. Answer is pretty simple. It is 2 by 3. What is derivative of sum of functions? So this something. So basically, if there are two sum of, whenever there's plus or minus sign, we find derivative of this term and we find the derivative of this term with the same sign is retained here. So the derivative of this function is this. It could be written as d by dx of x cube plus 4x square. Can be written as d by dx, just like opening the bracket, is x cube plus d by dx of 4x square. So this we very easily can find. What is derivative of this is pretty simple. Derivative of this function is 2. And what is derivative of root x? This also, I think one exercise, we had a square root function. And its derivative comes equal to 1 by 2 x raised to power minus 1 by 2. X raised to power minus 1 by 2 can be written as 1 by root x. So, and this also is a slightly tricky derivative, and we should be very sure of finding derivative of some root kind of terms. Right. Let's move on. Now we'll find derivative of division of functions. We have done product of two functions. So there is some, in case of product, there are two x terms, one in the, and they were getting multiplied. Here, one in the numerator, one in the denominator, something like this. And here also, numerator we take as u function, denominator we take as v. So there a uv function is u by v. So this in the numerator and this is denominator. So what is derivative of a function which is a division of two functions, u by v? It is equal to derivative, it is denominator into derivative of numerator minus sign. Numerator, derivative of denominator. Whole thing divided by square of denominator. This is a formula which must be memorized here. Because this is not very easy to derive. whatever is not easy to derive but very commonly used, you must memorize it. So this one, how we should start? There's a negative sign. We start with derivative. We start with the denominator function. Let's take one example how to apply this formula here. So even for if y is equal to y is given as 1 by sine x, can we apply a division function here? Yes, we can. Even the numerator also can be taken as 1 is a function and sine x is the second function. U is equal to 1 and v is equal to sine x. Numerator function is constant function, denominator function is sine function. We can do that also. So let's apply this case here. Can we solve this function here? So what would be dy by dx here? Dy by dx will be equal to denominator. Denominator is equal to sine x into derivative of numerator, which is 1, minus the numerator into derivative of denominator. Derivative of denominator sine x. And whole thing divided by square of the denominator function. Denominator is sine x, so sine square x. And you know how to simplify here? Derivative of constant is 0, so this term will become 0. It will be, and derivative sine x is, so it will be this minus sign, minus term here. Derivative of sine x is equal to cos x divided by sine square x, which can also all written as minus of cos x by sine x. So 1 sine x we written here divided by 1 by sine x, just for simplicity, because we are converting into cot function here. So this is equal to minus of cot x and by sine x cos x, inverse of sine x. So that's a derivative of 1 by sine x, or we can say this is a derivative of dy by dx of cosec x. Okay, so perhaps I've written here, this already here. I forgot this part, so maybe I erase what I have on ink on the slide. That's the derivative. Okay, can we find, so this is the term. Similar way, what are the other differentiation formula we should know? So far, what are things we have done? We are done with, start with something like this. Then we have also done derivative of sine x function. And after that, we had done product of two function. We had done a constant function. We had done division of the function. This is what we had done so far. So what are other things we need to know? Other formula. So we had done a sine function. In a similar way, we can find out derivative of cos function. Derivative of cos function is negative of sine x. Okay, and method derivation is very similar to this. So those who are interested can find it out. So what will be dy by dx cos x? Dy by dx will be equal to since it's cos function, cos of x plus dx minus of cos x divided by dx. And similar way, what we have simplified earlier for sine function, you find with minus sine x. And these are the functions which can be first. This can be derived using division function. How do we do that? D by dx of tan x can also written as d by dx of sine x by cos x. So it becomes u by v kind of thing, numerator by denominator, and it is equal to denominator cos x into derivative of numerator sine x minus of numerator derivative of denominator. That's it. And whole thing is divided by square of denominator quantity. What is there in the denominator? So we understand what is u here. This is u term, this is v term. There's a v square here, so it will be cos square x. We can simplify this part here. So derivative of sine x is equal to cos x, derivative of cos x is equal to minus sine x. So minus minus will become plus. So whole numerator becomes equal to cos square x plus sine square x is equal to 1. So it is 1 by cos square x, which is secant square x. So similar way, 1 by this also we can find out. This one sec x can be written as d by dx of 1 by cos x. So this also we can find out. But these two is something we are not going for derivation, but this is also common derivative we should remember. D by dx of log x is equal to 1 by x, and d by dx of e raised to power x is equal to ex. There is no change. Okay. So these are all the formula we need to know in case of differentiation or derivative. One last thing is chain rule in this session. What is chain rule? So chain rule is pretty simple. We want to find dy by dx. This expression can be multiplied by and divided by du. So this expression is same. Actually, what we have done, we have multiplied and divided by some quantity du. So it becomes equal to dy by du into du by dx. So this derivative has been expressed as product of two derivatives. So derivative of y with respect to u and derivative of u with respect to x. But why do we write something which is simpler in a complicated form? There's a reason for it. Let's see what the reason is. See, it looks fairly simple, but let's look at where do we use it, how do we use it, and why do we use it. This is typically used in problems requiring substitution. Let's see where we use it. Suppose y is given as not sine x. No, we are used to the formula y is equal to sine x. Derivative of that is cos x. It is not sine x, sine ax. There's some constant term. It is multiplied by this. So this is not a known expression. So we can convert into known form by suitable substitution. So how do we convert into simple form? What substitution is necessary to reduce this one into known form? We can substitute x is equal to new variable, not x, no, not y, is z. Let's say we make a substitution, ax is equal to z or z, whatever way to pronounce it. So if I make this substitution, this expression, y, here it is function of x, it becomes y is a simpler function of z. Y is equal to sine z. So now if I had to find dy by dx, let's see how we find out. We are still interested in finding what? We are interested in finding dy by dx. Let's see how do we dy by dx now. It becomes d by dx of, suppose I use this expression, it becomes d by dx of sine z. This I cannot differentiate because there's a to differentiate, if there's x here, this also has to be x, or if it is z here, this also has to be z. So what we do here, this expression we make d by dz of sine z and then dz by dx here. So I have multiplied and divided by dz. Now this expression is a known form and there's another expression here. So that's where we use substitution here to reduce an expression into a known form by suitable substitution. So let's do this substitution. Can we simplify this one now? This part is simple. What is d? This is similar to d by dx of sine x, which is equal to cos x. Since in place of x there is z term, it will be cos z. So this term is equal to cos z. And what is dz by dx is equal to? To dz by dx can be, again, let's put the value of second expression. Z is equal to ax. So dz by dx is equal to a. So this term is equal to cos z and this term is equal to a. And then I put the value of value of z. I again substitute back in terms of x. It becomes a into cos ax. So what you noticed here, whenever x term is multiplied by some constant here, again this constant here also, when we get the derivative, the constant comes out. Okay. So there's something, and if we are not clear what is happening here, we can follow step-by-step process. You do it few times, you will understand how to do it directly without going through the multiple step. So basically what we are saying here, what would be, see, based on this expression, can you guess what would be d by dx of sine of 4x? Well, this is again, this term is a. So basically what will happen, since it is 4x, derivative of 4x will come out. This will be 4 into sine cos of 4x. And we can do step by step, or we can understand what is happening here. A similar way, if you have to find d by dx of sine of 1 by 2x or x by 2 will be equal to, what is this constant comes out? 1 by 2, and again similar expression cross of x by 2. So this is where chain rule is, this is how the chain rule is used. This is necessary to reduce it to a known form. Let's look at one typical application of chain rule, which is used in mechanics, which is used in, kinematics, simple expression. Let's do that one. What is given here? Particle velocity is given as v is equal to 2x square. So depending on different position, it is moving along x-axis. So its velocity is defined as function of position. V is as a function of x. We need to find its acceleration when it is at x is equal to 1 meter. So, as a different position, velocity is changing. If velocity is changing, it means particle is having acceleration. So we need to find acceleration when it is x is equal to 1 meter. How do we find acceleration? The first thing we need to think of, what is acceleration? So do we recall what is acceleration? Acceleration is velocity is change of position, dx by dt. Acceleration is rate of change of velocity. That is dv by dt. That's acceleration. Instantaneous acceleration is dv by dt. That's what we need. So this is what we need to find. We put the value of v. So it is d by dt of 2x squared. You notice there's a bit of problem here. This is not x term here. So what we need to do, if I have to differentiate 2x squared, it can be differentiated since there's x term here. It can only be differentiated with respect to x here. So to do that, what I'll do here, again, multiply and divide by dx and bring this dx here and dt here. So what will be the value of acceleration term here? dv by dt, dx is 2x squared. So what we have done using this expression, it becomes d by dx of 2x squared into dx by dt. What is the derivative of 2x squared is 4x. Sorry, my bad. This is 4x only. For 2x squared, its derivative is 4x into what is dx by dt? Dx by dt is nothing but velocity. So it is 4xv is acceleration. But we need to find what is acceleration when x is equal to 1 meter. So when for x is equal to 1 meter, this x I will substitute 1 meter. But what is velocity when x is equal to 1? So we also need to find. So either I can substitute, if I want to find general expression, what I would have done in place of velocity, if I want acceleration as a function of position, I'll substitute velocity also in terms of position. In terms of velocity, I'll write 2x squared. So this would have become 8x cubed. That's the acceleration. So when x is equal to 1 meter, it will be 8 meter per second square. Or I could have substituted directly here. There are a number of ways you can solve it. So that's where chain rule is used. Chain rule is used in two cases: when to reduce any function to a known form by suitable substitution, and when the derivative, see this in this case also, when you have to differentiate a function with respect to some variable which is different, then also we need to apply chain rule. These are two typical application of chain rules. So this brings us to the end of second part of differentiation. So please go through multiple times so that you're absolutely clear of each and every part of this particular session on derivatives. I'll stop here. Thanks.